start with the recording. Share screen. Okay, so we started talking about superconductivity on Wednesday. So I gave you this picture that when there is actually a lattice deformation effect in the presence of the electrons, it can lead to a weak attractive force between electrons. So that would give you these Cooper pairs. And once the Cooper pairs condense, then that would actually lead to this zero conductivity material, and that's the superconductor. So first thing we try to do is to figure out how to couple electromagnetism to the Schrodinger field. We have been gotten pretty much used to that by now, but we need to make sure that we couple the electromagnetism consistently to Schrodinger field theory. So that's the first thing we try to do on Wednesday. And then we came up with this idea that you have to actually use this combination. So this is the analog of P minus EA you have seen in the quantum mechanics. Now it's in a field theory, and you write this particular combination to make sure that your Lagrangian is invariant under the gauge transformation. So for the spatial derivatives, that it comes always together with the vector potential. And for the time derivative, that always comes together with the scalar potential. And then you're guaranteed that this Lagrangian is invariant when you change the gauge. So gauge transformation, again, just a little refresher here, is that you change the scalar potential and vector potential by some arbitrary scalar function. I used the symbol chi on Wednesday. And you also change the phase of the field psi by the chi now in the exponent. And if you do both of them together, then this Lagrangian doesn't change. So that's the meaning of the invariance and the gauge transformation. And once you have that Lagrangian, then you can immediately work out the field equation, as again, we have done many times. If you take the variation of the action with respect to psi dagger infinitesimally, and demand that the action is stationary with respect to that infinitesimal variation, you find this equation here, and that's the Euler-Lagrange equation for the field psi. So in the presence of the condensate, of course, this psi can be solved as a classical field. So we try to understand the consequence of that. And without the electromagnetic field, so if we just set the vector potential and the scalar potential 0 for now, then this is the same equation we had before for the Bose-Einstein condensate. And we have found a special solutions for them. A static solution is just by going to the bottom of the potential given by this the chemical potential and this quadratic coupling lambda. And then this is the solution to that with an arbitrary phase. And so that's the same here as well. And just like in the case of BEC, you can also find a solution where the condensate is moving with a constant speed v. So that's another exact solution to this field equation. So these solutions are still there. And now that this field carries an electric charge, this solution with the condensate moving with a constant speed already carries electrical current. And so this is the electrical current that doesn't have any resistivity, and therefore this is what is called the supercurrent. So that's the superconductivity. So we have a condensate which has charge, and here I put E here, but for the case of the real superconductor, this needs to be 2E actually. So I didn't actually do that here because the Cooper pair is the condensate. So it carries the charge negative 2E, not just E, because it's the two electrons together. So you're supposed to put factor of 2 in here, which I didn't do, so I apologize. And so that once you actually put factor 2 here, that represents the condensate of the Cooper pairs, as we talked about, in the form of the BCS state. And when the condensate flows with the constant velocity, that carries electric charge, and therefore that's an electrical current. And electrical current without any resistivity is the superconducting current, or supercurrent, if you like. So that's the idea. So the solving Schrodinger equation so far is exactly the same thing you have done for the cold atom Bose-Einstein condensate that doesn't have electric charge. Here it does. But as long as there's no electromagnetic field involved, it's the same solution. So that's something you can find right away. Okay, so let me stop here. Any questions?
Yeah, did we talk about what causes lattice deformations?
So that's really electrostatic attraction between electron, which is negatively charged, and the lattice sites, which have the positively charged ions, because each atom has lost electrons that is now freely moving in a piece of metal. So each site is occupied by a positively charged ion. That's why there's the electrostatic attraction by the Coulomb force, and that causes the deformation of the lattice.
Okay.
Okay. Any
Thank
other
you.
questions?
What does it mean to talk about a current without the electric field?
So if this is actually just if you watch a so I think what you're saying is if there can't be a current without any external electromagnetic field. So you can actually, we will talk about this in a moment. You can actually think about this donut-shaped the tube, just like we talked about in the case of Bose-Einstein condensate. And initially, you probably place a magnetic electric field to start to let the current flow. But once it starts flowing, you don't need the electric field anymore. You just turn it off. And then it keeps flowing because there's no resistivity. And I will show you the data, how long it can keep flowing. There's a data that shows that this supercurrent can keep flowing more than 100,000 years without any external electric field. So you turn the electric field off, then it keeps flowing, and that would correspond to this solution with a constant velocity.
Okay, so, but the charges would, the moving charge would produce its own field, right?
That's right. So once there's a current, then of course it creates a magnetic field. So that's not the external field you apply, but the supercurrent itself would create magnetic field because of the electric current going. So that's not external magnetic field because you don't apply it, but the current itself creates the magnetic field. And we will talk about that too. Okay. Any other questions?
So what causes it to slow down after a very long time? Because I know that.
Right. So again, this is topological protection because it turns out the electrical current is also quantized in this case. And then that actually requires a tunneling from, let's say, number 10,000 to 9,000, 10,000, 9,999 and 9,998. So that's a tunneling process. That's why it doesn't happen quickly. It's very slow, but it is possible to have this tunneling process. So that's how it starts to slow down over a long period of time. So it's not a continuous slowdown because there's no resistivity and it's quantized. So there's no a way to go from a 10,000 to 9,999.8. So you can't do that. It has to jump. And that jump happens by a tunneling process. And you can keep having this tunneling process. And over time, it would eventually go to no current. But that's because of this topological protection, it takes a long time. And I show you the data later.
Okay.
Okay.
Thanks.
Any further questions? All right, so this is a situation when you don't apply external electromagnetic field, you can have this static condensate as a solution or moving condensate with the current flowing because of the electric charge. So now we come to this persistent flow. So this is the slide I have shown you in the case of the Bose-Einstein condensate without any electric charge. That's why this derivative doesn't have any vector potential in it. And we did this the Gedanken experiment putting the Bose-Einstein condensate into this donut-shaped tube, and we switched to the polar coordinate. And this is the expression of the derivative in the polar coordinate. And because the whole thing is stuck inside this tube, we don't care about this motion in our direction. And also we make sure that this field psi is periodic by 2 pi in this azimuthal direction. And we forget about this R derivative. And then we can immediately solve this solution where we found that this N, that's basically the momentum in the azimuthal direction, to be quantized because of this requirement of periodicity. And so this describes the flow, the superfluid flowing along this azimuthal direction inside this tube. And given n is quantized, there is a special topological protection. And we have discovered that the circulation of this flow, which is defined by the velocity integrated along the direction, the line direction, is actually quantized in the unit of h/m. So that's what we have talked about in the case of a superfluid. And now we apply the same argument to superconductor. So we now have the derivative replaced by the covariant derivative. So there is vector potential and scalar potential now coming into play. But this periodicity is still true, just the fact that it is inside this periodic tube. So there is quantization going on as well. So you were talking about some integer that would characterize the flow of the supercurrent inside this tube. So what we like to do is to see the consequence of that. So here we go. Now we have this new Lagrangian, which has the covariant derivatives. This is the field equation we derived just on 2 slides ago. And we put that into this, again, donut-shaped tube. And here is the field equation now written in terms of the polar coordinate. I already removed the direction of the radius because we decided not to think about it. So this is only derivative along the azimuthal direction. So the azimuthal direction is theta, and derivative along this azimuthal direction is, of course, accompanied by the azimuthal component of the vector potential, which I denoted by a theta. Then we also made sure that the charge is now 2e. So the first line is wrong. I'm sorry again. I should have put the factor of 2 in there as well. But the rest of the equation is correct. So the field equation has charge 2e. And now in polar coordinate, charge is 2e in front of the azimuthal component of the vector potential. And then we try to solve this equation now. Now, there's something new here. So if you take this solution where the periodicity comes with the integer n again, so n is again integer. So here we go, n is an integer. Then this theta derivative inside this field equation will pull down n from the exponent, right? So this d theta is in, just because it acts on psi. Now we have an interesting solution where in here is canceled by the vector potential in theta direction if you take this configuration here. So if a theta is given by this value, then things in the parentheses completely cancel against each other. That means you can have a static solution now because this cancels. And for this value of the condensate square root of mu over lambda, the last 2 terms cancel against each other. So everything on the right-hand side now is 0. And therefore, left-hand side should also be 0, which means the psi is now time independent. So this is a solution which we didn't have before for a superfluidity because there was no vector potential. So everything here now cancels. So the field equation is satisfied by 0 equals 0. So that's the way it works here. And the reason why this is interesting is that this really represents the situation, I think, what Shiraz was asking about, namely that this, of course, represents the current with the electric charge flowing in through this tube. That means there is now the electrical current flowing, which, of course, leads to the magnetic field. And that magnetic field is actually given by this A theta as a part of the solution to this field equation. So that actually gives you the idea called flux quantum, namely that if you compute the magnetic flux going through this hole inside this tube, that's the area integral of the magnetic field. And using the Stokes theorem, area integral of the magnetic field is the line integral of the vector potential. And I think going from line integral to area integral is easier to understand. The line integral using Stokes theorem can be written as the area integral of the curl of what's integrated along the line. The curl of the vector potential is nothing but the magnetic field. So that's how you see this equality, namely that area integral of the magnetic field, which is nothing but the magnetic flux, is given by the line integral of the vector potential along this perimeter of this tube. But one thing we learned is that this A theta, the vector potential in this azimuthal direction, is now quantized in the unit of h/2e. So you just plug that in here. It doesn't depend on theta. So d theta integral just gives you 2 pi. And 2 pi times h bar is h, the Planck constant. So now you find that the total magnetic flux that goes through this hole inside this donut-shaped tube is quantized in the unit of h/2e. That's the idea of the flux quantum. So this is the solution that would describe the supercurrent flowing inside this tube. That's the constant current that carries electric charge around this tube, together with the magnetic field punching through this hole inside this tube. And the current itself is quantized because that comes with the integer n. And correspondingly, the magnetic flux going through this hole inside this tube is also quantized in the unit of h/2e. So this is actually very useful. So we use this idea that what can condense for electron has to be a pair, because the electron is a fermion. It cannot condense on its own. It cannot occupy macroscopic number of the same states. But once you create a pair, then you can talk about the macroscopic occupation number for the pairs with the total momentum 0. And that's why we're talking about the condensate with charge 2e. But now you can actually test this experimentally, namely that if you measure the magnetic flux going through the hole inside this tube, and if you verify that it is indeed quantized in the unit of h/2e instead of h/e, that is an experimental evidence that the condensate is really made up of pair of electrons, not electrons singly, but pairs of electrons. And indeed, the data do show that. So by measuring the flux quantum to be in the unit of h/2e, you have now a proof that the condensate is indeed made of pair of electrons with charge 2e, and that's exactly what had been discovered. So that's how we know that the superconductivity is really due to the condensate of Cooper pairs, each pair with charge 2e. Okay, so let me stop here. So this is almost the exact analog of the persistent flow we talked about in the case of the neutral atoms, Bose-Einstein condensate. Now we are talking about the condensate of Cooper pairs. And because the Cooper pairs carry electric charge, this supercurrent in this tube is accompanied by a magnetic flux, as you would expect. And this is not the external magnetic field. This is a magnetic field induced by the current. And that magnetic field is quantized in the unit of h/2e, which turns out to give you an experimental evidence that this is really due to a supercurrent which carries charge 2e because they correspond to the Cooper pairs of electrons. So that's the idea of this persistent flow in a case of superconductivity. So the main difference, as I keep saying, is this presence of the magnetic field induced by the supercurrent, which didn't exist in the case of the neutral Bose-Einstein condensate. But now that we are talking about the condensate with charge 2e, it does lead to the magnetic field, and that comes with this flux quantum of h/2e. All right, I stop here. I'm sure there are questions. Shirad looks like ready to ask a question.
Yeah, I was just wondering, I have two questions. So one is, so this entire tube has to be made of the lattice, right?
Right.
For the Cooper pairs.
So
to
you
flow.
basically create a tube-like ribbon made of, let's say, some kind of metal, like niobium. Yeah.
Okay. My second question was, Yeah, I still don't fully understand what it means for there to be this time-independent solution.
Yeah, so maybe a little counterintuitive because the current is flowing, so the electrons are moving. So it looks like, you know, this should be time dependent. But in some sense, just the current going around is a static situation overall. Just like in the case of quantum mechanics, the stationary state actually does not depend on time in a sense that the physics remains constant over time. So in the same spirit, this flowing current as a whole is a static solution to the field equation. So it doesn't evolve over time. This is really a situation where physics remains the same as a function of time. So that's the time independence of the solution over here. Does that answer your question?
Yeah, I guess just like with the BEC, it seems like we had essentially the same thing. So I'm trying to understand what the difference is.
Yeah, so the BEC case, the solution was indeed time dependent. So that's why you of course you deserve to be puzzled by that. So we found this solution, which is still time dependent. But again, when you actually look at some observable, for example, the density psi dag of psi is actually canceled this time dependence here. So the observables actually are always time independent. So in the same spirit, so this time dependence just by the overall phase in that sense doesn't actually do anything really. So in this case, you do find a solution which doesn't have time dependence at all. But whether there's a time dependence as the overall phase or no time dependence, it's either way, that's a sort of static situation as far as the physics is concerned. So in that sense, you know, it doesn't really matter where there is an overall phase that depends on time or not. Okay. Any other questions about this? So again, you know, just to emphasize this point that the only thing we did is take Schrödinger field theory and promoted all the derivatives to covariant derivatives. That's the only thing we have done. But that alone already give us an idea that you can have this superconductivity. And in addition, you have this quantum of the magnetic flux directly as a consequence. We didn't put any new ideas into this. Just take the Schrödinger field theory at the face value, now promote it to the covariant derivatives. That's the only thing you need to know. And that leads to this idea of the persistent flow together with this flux quantum. And the presence of flux quantum really nails this point that when, for example, n degrades to n-1, then the magnetic flux has to jump from a certain size to a certain smaller size. And that happens only through a tunneling process. And that's why it is sort of protected. The tunneling is always exponentially suppressed. And that's why the current can keep flowing for a long period of time. And that's shown in this data here. So in this experiment, what they have done is to have this tube wrapped around by a band made of superconductors. So here you have these the coils made of the cables out of the superconducting material. So each little circle here is actually a cable, and that goes around this tube. And that's the analog of the tube we talked about on the previous slide in this picture. Now this is a real thing. So you have this superconducting wire going around this tube. And then you let the supercurrent start to flow by, you know, applying electricity or whatever. And then you just watch it for a long period of time. And in this particular experiment, this superconducting wire is made of an alloy made of niobium and zirconium. And they watched how the current may degrade over time. And you're already talking about a long time scale. This is 240 hours, that's 10 days, 20 days, 30 days, 40 days. And this is the field, magnetic field going through this tube. and that's meant to be quantized. It's a big number over here. So the change in this is actually looks almost continuous, but it is meant to be actually a step function all the way through because it can only jump. You don't see those steps in this, but anyway, so that's the idea. And then by measuring this slope, you can tell when this current would completely die off. And it's exponential. And that exponential slope gives you basically a lifetime of this current. And that data turns out to be longer than 100,000 years, as I mentioned a couple of minutes ago. So this is the meaning of the persistent current. It's not infinite because you can still tunnel and make the current smaller over time, but it can go on for a long period of time. So that's how good it is to have zero resistivity. If there's any finite resistivity, like in normal metal, then it just keep going down very quickly because all the energy of the current would basically end up being heat because of the resistivity, and then they just all dissipate away. But that doesn't happen here because there's zero resistivity. The only way you can lose current is by tunneling from certain n integer to n-1 to n-2. Each process of tunneling is exponentially suppressed. That's why it can happen only very slowly. And therefore, it ends up being a very, very long lifetime of the current, which you can measure as a macroscopic current and macroscopic magnetic field in your experiment. And this macroscopic current is really protected from decaying over a long period of time. And that's the idea of the superconductivity. And so this is really amazing. You can have this macroscopic current flowing, which does lead to macroscopic magnetic field. But because of the quantum nature of the electrons being in Cooper pairs, that's a highly quantum phenomenon based on this condensate of the Cooper pairs. They are protected. There's no resistivity. It decays only by this tunneling phenomenon, and it can go on for a long period of time without dissipating heat. And that's why you actually use this for things like a MRI in hospitals, medical resonance imaging, because you like to create a very high magnetic field, many Teslas, to look into your brain with the nuclear magnetic resonance, right? So to produce that kind of magnetic field, you would like to make sure that the power doesn't get lost. Otherwise, your apparatus becomes incredibly hot. You don't want that. And that's why you use superconductor at a hospital. You use the same thing for creating magnetic field in Large Hadron Collider at CERN. You would like to apply this 8 Tesla of magnetic field to keep bending this very high energy proton beam along this circular tunnel. And again, you don't want to create huge amount of heat for this. You would like to also save power. And that's why you use the superconductor, in that case, niobium titanium. And that's how you can create very strong magnetic field without energy loss in a sustained fashion. And that's how things can work. So this is really the quantum physics working in action on a macroscopic scale, which can be actually used for practical purposes like this MRI and the Large Hadron Collider. And it's very much sustainable because of this topological protection going on. So that's the idea. And I thought about this already many times, so that each time I still find it really incredible. Quantum physics in action on macroscopic scale. And that's actually even useful for practical purposes. All right, so let me pause here again. I'm sure you got some questions, Riley.
Oh, yeah, I have a question. So what we're seeing here is the flux tunneling from n to n-1.
Mm-hmm.
Is it possible, I have like two questions. Is it possible to skip an n-1 and go straight from n to n-2?
I suppose so. Yeah, that's of course more suppressed in terms of probability.
Less probable.
Yeah,
okay.
Yeah, but it can happen in principle. Yeah.
And is it also possible to maybe like excite from -1 to n? In the
of course, that would cost energy, so you have to supply energy to make that happen.
Okay, makes sense. Thank you.
Any other questions? Okay. Yeah, I hope this data is convincing, right? It's, this is really a demonstration that there's zero resistivity for this supercurrent. Otherwise, it can't last for 100,000 years. So, I keep repeating myself, but this is really a phenomenon due to really highly quantum effect of matter, namely electron in this case, that will lead to this topological protection, that will lead to zero resistivity. And that's a macroscopic manifestation of the quantum phenomenon, which actually turns out to be useful for practical purposes. And I still find it incredible. And let me also look at the case when you have just a piece of superconductor rather than this tube. You just have just the material in front of you, and then think about how the magnetic field gets affected by it. So in this case, I'm not applying a current, but I would like to see how a magnetic field would behave close to a piece of superconductor. So in this case, you have to put in this Lagrangian for the Maxwell field as well. And I don't know if you have seen this before, but for the Maxwell field, you can derive these Maxwell equations out of this Lagrangian, which basically looks like E squared minus B squared. And what you're supposed to do is to regard this E as written as a function of the scalar potential and vector potential. B, of course, is the curl of the vector potential. You take the variation of this E squared minus B squared with respect to scalar potential and demand the action is stationary, and that will lead to Gauss's law. If you vary this action with respect to the vector potential, and again demand that action is stationary, that stationary condition would lead to this last equation of the Maxwell's equation. And the middle two equations are just consequences of the fact that E and B are written in terms of scalar potential and vector potential. Because B is the curl of the vector potential, its divergence is automatically zero. E is minus phi dot minus grad phi minus A dot. B is curl A, and the grad phi curl of that identically vanishes because curl grad of function is always zero. Minus A dot in here and curl is the same thing as B dot with plus sign, so they cancel. So that's automatically zero. So the two middle equations in Maxwell's equations are just a consequence of the fact that you can write E and B in terms of scalar potential and vector potential. But the first and fourth equation is really the stationary condition coming out of this Lagrangian E squared minus B squared. So I don't know if you have seen this before, but the Maxwell equations are a consequence of this simple Lagrangian, which is written as E squared minus B squared. So that's how you can derive the field equation now. So now that the electric field, magnetic field couples to the Schrödinger field through these covariant derivatives, we can write down Maxwell's equation in the presence of the Schrödinger field. And that's the important piece. So here, this is supposed to be J, but now you can derive what J should be in terms of Schrödinger field by taking the variation with respect to the vector potential. So that's how you can derive the field equation. And psi dag of psi has a meaning of the number density. So this rho ends up being 2e times psi dag of psi. And that's obvious because you take the variation of the Lagrangian with respect to scalar potential to derive this Gauss's law. And variation with respect to scalar potential of this E squared term is what gives you this divergence E. But scalar potential is also here. You take the variation, and that would then give you minus 2e psi dag of psi. So that's how you know this rho should be 2e psi dag of psi. And you also learned what J, the current, should be by taking the variation of the Schrödinger quantum field theory Lagrangian with respect to vector potential. And by taking variation with respect to this one, you get psi dag grad psi. By taking variation with respect to this extra A over here, you get grad acting of psi dagger times psi, that's the second term here. But there's also a piece which is the product of two A's. So taking variation with respect to A, you get a factor of 2 out of that. So that gives you this 4E term times psi dagger psi. So that would be the expression for the current of the Schrödinger field. And when you think about situation when you have this condensate, constant in space and time, then psi is the constant given by square root of mu over lambda. And so this is now constant, so this grad psi vanishes in that situation. Then the only piece that would remain is this piece that doesn't have derivative on it. Psi dagger psi is the number density itself. So when you have the vector potential, when you have magnetic field, for instance, then you have a current proportional to that. And this is a situation which is unusual, because when you actually write down this the Maxwell's equation, this last equation over here, the curl of B in the case of static field should be given in terms of the current. And when you write out this curl of the magnetic field with the vector potential, it's just a vector calculus, you find the piece, two pieces over here. One is the divergence A and the gradient of it, and the other piece is the Laplacian of A. And when you take a simple gauge like Coulomb gauge, this is the divergence of A that is supposed to vanish in a Coulomb gauge, so that goes. And this is the electrical current we derived from the Schrödinger field. We took the constant condensate, so the current was simply proportional to the vector potential itself. And you find this unusual equation that the Laplacian of the vector potential is given by vector potential itself. And this is actually easy to solve. Laplacian giving you just a number is immediately solved by just it is exponential damping function. So if A, vector potential, is this exponentially damping form as a function of space, then this Laplacian basically does the derivative twice, acting on this x, pulling out this 1 over lambda L twice. So lambda L twice should be given by this constant over here, given by this density. So taking derivative twice, I get 1 over lambda L twice. So this Laplacian turns into 1 over lambda L squared, which is supposed to be given by this mu 4e squared over m n. And I apologize, this mu is actually not chemical potential. This is meant to be magnetic permeability. In vacuum, that's mu naught. In material, it may be different from mu naught. That's why I use the symbol mu, which clashes with the notation of chemical potential. I wasn't aware of this. I'm sorry about this, but I hope this is clear. This is the magnetic permeability inside this material of the superconductor. So now you work out what this lambda L should be, and that's given by this combination. That's just the inverse of this in square root as a solution to this Maxwell's equation in the presence of the condensate. So what you learn here is that the magnetic field, as a consequence, damps exponentially into the superconductor given by this finite charge density n. And this is exponential damping behavior. What it means is that magnetic field does not penetrate into a piece of superconductor. It only penetrates into the skin by a finite distance. And you can go ahead and estimate this finite distance, which is of the order of things like a micron or so. So it's a tiny, tiny distance. So magnetic field is practically expelled from a piece of superconductor. And that is the famous Meissner effect. Magnetic field doesn't get into the superconductor. So if you do the experiment in your laboratory, and before you start to cool the system, above the critical temperature of the superconducting phase transition, magnetic field does get in to a piece of metal. But as you cool the system, and once you go through this phase transition, then it becomes a superconductor, and all of a sudden, magnetic field gets expelled out of this material, and that's the Meissner effect. And you might have done this experiment in the laboratory. And it's not completely expelled. It does get into the skin by a finite distance given by this lambda L, which is called the London penetration depth. I'm sorry, I went ahead of myself. The London is the name of the person who first wrote this equation. He didn't know this theory of the condensate back then, but he observed experimentally that the magnetic field is being expelled. To expel magnetic field, the equation should look like this. So he sort of came up with this equation empirically and without any derivation from theory. And this is what is called the London equation. And as a solution to the London equation, you successfully do find this exponentially damping behavior of the magnetic field, and hence London penetration depth, namely, this was discovered by Mr. London. This is how much the magnetic can penetrate, and the depth of the penetration is given by this lambda L, hence London penetration depth. So that's the origin of the name. But idea is simply that now we discover, just by introducing the covariant derivatives to a condensate in Schrödinger field theory, you find that magnetic field gets expelled as a consequence of this covariant derivative together with the Maxwell's equation. So you would predict now, just by having Schrödinger field theory with the covariant derivative, you now predict the magnetic field should be expelled as a consequence of this. And that's now you can understand it theoretically, why this Meissner effect happens. Okay, so let me stop here again. So I hope that at least the argument is clear, and please ask questions.
The first expression for J for the current is we got by taking the variation with respect to A.
That's right.
To the vector potential from the entire Lagrangian.
So we have A dependence here, there, and also in E and B. We know variation with respect to A from this E squared and B squared is what gives you this curl B minus 1 over C squared E dot. That's the Maxwell's equation. But A dependence is also here now in this covariant derivative acting on the Schrödinger field. So I need to take variation with respect to this A and that A as well. Then you derive this expression. So there is no additional input. It's just a consequence of the covariant derivative. There's no ambiguity, there's no freedom. So this is the expression now you predict out of the Schrödinger field theory. Then all I have done here is that now you have this ball made of superconductor. We know there's a constant condensate in there. So I replace this psi by this constant condensate. Then all these derivatives go. You have this piece coming from constant number density n. That's now your prediction on how the current should look like in the presence of the vector potential. But now that the current depends on this vector potential, you find this interesting equation here, that's a London equation, namely the Laplacian of the vector potential is vector potential itself. That will lead to this solution that is exponentially damping, and hence only a skin depth of penetration of the magnetic field into superconductor, and that's the Meissner effect.
Okay.
Do you actually do this kind of experiment in the physics 111? No? Maybe it's coming at some point. I'm sure you do this in the physics lab experiment. Okay, any other questions here?
Yeah, I have. Sorry, my
Okay.
being weird.
You're very soft. Can you get closer to the microphone?
Is that any better?
It's better, yeah.
Okay, sorry, my internet is being really strange right now.
Oh, is that right?
But wondering, like, with the seeing how the Maxwell equations come out of this Lagrangian, is it like, do we want to understand the Lagrangian as coming from the Maxwell equations, or do we want to understand the Maxwell equations as as coming out of the Lagrangian?
Well, historically, of course, people came up with these equations first.
Right.
And once you know the equations, you can walk backwards to see what Lagrangian would reproduce Maxwell's equations. And historically,
Right.
that's the way it happened.
Right.
But from modern point of view, you write the Lagrangian and you find the field equation as a consequence. It turns out, and we will see that later once we actually put this together with relativity, the electric field and magnetic field is a Lorentz covariant tensor called F mu nu. And the only Lorentz invariant combination you can write turns out to be this E squared minus B squared. There's nothing else you can write down as required by Lorentz invariance. So you know ahead of the time, if you are dealing with a field strength, E squared minus B squared is the only thing you can write down in your Lagrangian. And if that's the case, you would predict the Maxwell's equation should look like this. So now we learn the Maxwell's equation as a consequence coming out from theoretical argument. So that's not the way that historically was discovered. Historically, you know, the Faraday discovered the concept of field, and then there was the discovery of the magnetic induction, and then Maxwell came up with all these equations, and apparently he was thinking about all kinds of gears moving around in space because they are all vectors. And that's how somehow he came up with this ingenious idea that this has to be the right equations. And so that's how we discovered Maxwell's equations. And to get Maxwell's equations, we need this Lagrangian. That's the way that historically it happened. But from the modern point of view, it turns out if you want to write down the Lorentz invariant action for the field strength, this is the only thing you can write. And it turns out that that will lead to Maxwell's equations. So now you know why the Maxwell's equations should look like they do. And that's how we understand it from modern point of view. Does that answer
So
your question,
we like
Dorothea?
can understand Maxwell's
Mhm.
equation.
Yeah.
Yeah, so like we can sorry, I was saying we can understand Maxwell's equations as like coming out of QFT.
Yes, that's right.
That's so cool.
Yeah. So that's the way we understand things these days. Okay. Any other
Thanks so much.
questions? Yeah. Yeah. It is really cool, isn't it?
Yeah, that's so cool.
Great. Any other questions?
Yeah, I have sort of a follow-up to that. I was just
Okay,
it seems like with the Maxwell Lagrangian, the scalar potential and the vector potential are canonically conjugate. Is that true?
To be precise, what is canonical conjugate is the vector potential and its time derivative. So if you look at the E squared,
Okay.
E is the negative grad phi minus A dot. So if you take derivative with respect to A dot of this Lagrangian, then what comes out is E. So I think I misspoke. So what is canonical conjugate to A is E. That's the canonical commutation potential you're supposed to set up. And we will do that later.
Wait, okay, sure.
And that's an excellent question because that shows you really understood the idea of canonical quantization now. Once you see a Lagrangian, that's the first thing that would come to your mind, and that's indeed, it did occur to you. And then you identify the canonical conjugate momentum, and then set up the commutation relation and start building the Hilbert space. And we will precisely do that in next week. Okay. Thank you for asking that question. Any other questions? Okay, so now we learn the magnetic field gets expelled by the superconductor. But in some cases, they are not totally expelled. In addition to this exponentially suppress the penetration into it. And that's when you have what is called the Abrikosov flux. And that's actually the same idea when we talked about vortices in superfluid. So when you have this condensate, you can try to look for a solution where at spatial infinity, psi rounds around the phase by integer times at the spatial infinity. And that's how we discovered the vortex solutions in the case of superfluid, right? But now that you have this coupling to the vector potential, when you round around when you go around the phase by once at the spatial infinity, in order to minimize the energy of the system, at infinity, you want to make sure that this covariant derivative vanishes. Now the psi doesn't vanish, then it can actually lead to a constant. Then you would have the infinite energy growing the volume of space, and that's not what you want. You want to make sure that this combination actually vanishes at the spatial infinity so that you can find a solution with a finite energy. So what that tells you is that this gradient, which does act on this azimuthal angle theta in space, should be canceled by this 2EA. And that's exactly the same thing you have done already in the case of the superconductor in a tube, right? So I can use the same solution. Psi at spatial infinity goes around once in its phase. Then the derivative should be compensated by the vector potential in this azimuthal direction. And what we discovered is that in that case, the total magnetic flux is quantized in the unit of h/2e, which can now happen without a hole. You have a piece of contiguous bulk superconductor, but once you take this kind of boundary condition at an infinity, you see a magnetic flux punching through it, and hence the flux predicted by Mr. Abrikosov flux. And we can go ahead and solve again. This field equation is a nonlinear equation because you have this quadratic term. And I can solve this analytically, unfortunately, but numerically, it's not a difficult equation to solve. And here's a solution. So at the spatial infinity, psi approaches the constant value as predicted by these potential terms, square root of mu over lambda, so that this potential energy is minimized at spatial infinity. But when you close to the origin, then it doesn't have to be at this value of the condensate. It can go all the way down to 0 at some point in space. And horizontal axis is just the radial direction. And azimuthal direction is given by this theta dependence over here. So I'm not plotting it. So if you go around the circle, then this value of psi would change its phase. Here, I'm just plotting the magnitude of psi. And so at spatial infinity, it has to approach the value of the condensate to minimize energy. But at the origin of space, it may go to 0. And at the same time, you solve for the vector potential as well. So you are now solving two coupled differential equations for field psi and A together. And so that's why you have to solve it numerically. And this is a solution for A in the azimuthal direction, a theta component of it. So both psi and A vanish towards the origin. And at an infinity, A of theta should approach the value to cancel the theta derivative of psi, just like we have done in the case of the donut, right? So that's the value constant over here. So at the spatial infinity, that would cancel this covariant derivative of psi. So then the kinetic energy term goes to 0 at spatial infinity, and you can find a finite energy solution because of that. So this cancellation is guaranteed by choosing a particular value of A of theta. So here I use the vertical axis in such a way that A of theta approaches 1. And that actually is meant to be, I forgot, h/2e, I guess, for the theta component of A. So that's meant by 1 here. Psi approaches also 1, that is in the unit of square root of mu over lambda. So they both approach 1, but in a different unit. And but at least that's the way you can see that they are really approaching constant at spatial infinity. But now that you have solved for A of theta, you can compute its curl, and that's the magnetic field in green. So magnetic field penetrates through the superconductor where the vortex is. but it dies off exponentially. So it's punching through the magnetic field, punch through the superconductor in a very, very localized fashion. And the total magnetic flux that goes through the superconductor, again, can be computed by the line integral of the A theta using Stokes' theorem, which precisely cancels this derivative. We know it's 2h bar over 2e. So the theta integral gives you, again, h over 2e. So now you have a situation where the supercurrent is going in a circle. You can take this solution we just discovered, put that into the definition of the current we derived on the previous slide. And I just plotted the current, and it looks like this. So you can really see that this is very similar to the vortex we had for the superfluid, but now this vortex carries electrical current. So this is really electrical current flowing, again, without any resistivity. And in the middle of it, so that looks like an eye of a typhoon or a hurricane, and that's where the magnetic flux is. And that's a solution to the Maxwell equation, because now that there's an electrical current, that should induce magnetic field, and there we go, there is a magnetic flux. And that's a solution to both the field equation for the Schrodinger field, as well as the Maxwell's equation. And the magnetic field then dies off exponentially, and that's again because of the London penetration depth. But in the middle, you do have the finite flux, and we know that has to be quantized based on the same argument we did with the tube of the superconductor. And that just comes from the fact that the phase should come back to the original phase by going around this circle in 2 pi. So that's an integer. Here I'm using integer to be 1 as a simplest example. And that's what you predict such a solution should exist. And that's what Abrikosov really did predict. And then it was discovered in the end. For certain type of superconductor, that's not for all type of superconductor, such a magnetic field penetration can happen. So there are 2 types of superconductor. One type is called type 1. For type 1 superconductor, it turns out that these vortices would attract each other. And then once you have the magnetic field going through, then they would all come together and bunch together into a macroscopic size of the magnetic field that would destroy the superconductivity. So you go from the phase of superconductor, and if you apply magnetic field, there's a phase transition where the superconductivity is broken and goes back to the normal material. So that is called type 1 superconductor. And this is the kind that had been discovered first by Onnes in Netherlands a long time ago. But according to Abrikosov, there can be a different type of superconductor called type 2. Namely, you start with a state that doesn't have any magnetic field going through it. Magnetic field is being expelled. It gets only into the skin of the material on the surface. But as you increase the magnetic field, expelling the magnetic field would cost you energy because magnetic field gets concentrated on the edge, and the energy of the magnetic field goes like B squared integrated of volume. So it costs you energy to expel it. At some point, becomes energetically more favorable to let the magnetic field punch through the superconductor in these vortices. And the vortices, again, end up having a very nicely arranged triangular lattice, just in the case of the vortices in the superfluid. And so that is what is called a mixed state. So you have a piece of superconductor, but inside the superconductor, you have an array of these vortices, and each vortex has a magnetic field punching through it. And when you increase the magnetic field even further, then even that is energetically not sustainable, and eventually you do another phase transition into a normal material. So between normal material and a superconducting state, you now have a mixed state. You have bulk superconductivity, but inside the superconductivity, you have these magnetic fields punching through them. And when the magnetic field punches through the superconductor, as we saw in the previous slide, condensate vanishes. So you destroy superconductivity, but only locally, where the magnetic field punches through the superconductor. So that's the idea, that now you have this supercurrent flowing in circle, and there's an eye of this current, like in hurricane. That eye is where the magnetic field punches through the material. That is where condensate also vanishes. So there's no superconductivity in the middle. You do violate, destroy superconductivity because of the magnetic field. But you can do that, and then you have only locally magnetic field punching through it. It dies off exponentially, given by this London penetration depth again, and then total magnetic flux going through this the vortex is given by this quantum flux of h/2e. So that's the idea of this Abrikosov flux. So the idea is very similar to vortices in superfluid, but what is quantized here is not circulation, like in the case of superfluid, but rather the magnetic flux that is quantized here. And again, this magnetic flux is quantized in h/2e because of the Cooper pairs carrying charge 2e instead of h/e. And depending on the material, you have a situation whether these magnetic fluxes would attract each other, then that would become a macroscopic magnetic flux that eventually destroys the superconductivity completely. Or in case where these parameters give you magnetic fluxes repelling each other, then each magnetic flux in a single unit of h/2e stays away from each other as much as they can, and they neatly line up into this triangular lattice, and that gives you this mixed state. And indeed, it looks like this. This is a triangular lattice of the magnetic fluxes trapped inside this vortex, each with a unit of h/2e. But because they repel each other, they would like to be as far away from each other as possible. They socially distance and line up in this neat triangular lattice, just like what we have seen in the case of vortices in superfluid. So that's the prediction now, which is now confirmed by this experiment. So you take this certain material of the type 2 superconductor, which has these parameters where magnetic vortices repel each other. You apply magnetic field. Up to some point, magnetic field is totally repelled by the Meissner effect. But beyond the critical value of the magnetic field becomes energetically more favorable to let the magnetic field penetrate through the superconductor using these vortex solutions of the Abrikosov flux. And then they line up neatly into this triangular lattice. And as you keep jacking up the magnetic field, this lattice becomes denser and denser. But beyond certain critical magnetic field again, you can't sustain these vortices anymore. And then superconductivity now gets totally destroyed, and then it goes back to this normal material. And that's the second phase transition. So from zero magnetic field, you increase the field, and it stays repelled. And beyond this field, now penetrates through the superconductor in these vortices of the triangular lattice. And once you get to this critical value of the magnetic field, then finally superconductivity is totally lost, and the material turns back into the normal material. So that's the idea of this type 2 superconductor. So I showed you 3 slides altogether because otherwise it probably wouldn't make sense. But everything again is predicted. Once you have the Schrödinger field theory, the only thing you have done is to change the derivative by covariant derivatives. That's all you did. But then you do find the solution to the field equations, classical field equations, I emphasize again, which is given by these numerical solutions right here. And this is a highly quantum material made up of electrons inside the metal, just like the quantum physics of the Bose-Einstein condensate of cold atoms. But using field theory, classical field describes this highly quantum material. All you have to do is just put this differential equation, classical field equations into your computer and solve it numerically. And this classical field equation really represents the state of highly quantum material with this Cooper pair condensates now together with the magnetic field, and you predict such a solution should exist. And that's this solution shown numerically over here. And then we predict such a material can happen. And then I have shown you the experimental data where that does happen. So that's how we understand this behavior of type superconductor together with these vortex solutions with a quantized magnetic flux called Abrikosov flux, named after the discoverer, and who got Nobel Prize for this, I think not a long time ago, maybe 15 years ago or something. Okay, so any questions about this whole business of the Abrikosov flux? I hope this analogy to the vortices we have seen for the Bose-Einstein condensate is helpful. I hope so. No questions? And whether you have type 1 superconductor or type 2 superconductor, is basically a competition between this repulsive force, lambda, and the electromagnetism. So depending on the relative size of this repulsive force given by this psi to the fourth term in the Lagrangian, and electromagnetism described by the size of the charge of Cooper pairs 2e, depending on which force is stronger, you can have either type 1, where the vortices attract with each other and destroy the superconductivity completely, or the vortices repelling each other, so that you can have this vortices punching through the superconductor, staying away as much from each other as possible, forming a triangular lattice. So it just depends on the nature of the material, how strong the repulsive force is among the this condensate of the Cooper pairs. No questions? Everything clear? Okay, so this is the picture of these magnetic vortices punching through a superconductor for a thick superconductor. You can also study the case where you have a thin film of a superconductor. And if you have a thin film, then magnetic field penetrating through it is sort of like a little dot because it doesn't have much of a depth in the vertical direction. And you can observe that these fluxes can actually move around in that case. And they're called fluxon, as if it is a particle. The particle is often made with on, like electron, muon, right? On is a particle made of magnetic flux, so that hence fluxon. And here's one picture of it.
We are looking at an array of defects. When the magnetic field is applied, vortices are produced from the upper film edges, and the front row of defects is soon occupied. However, subsequent vortices cannot easily pass through the front row. When the vortices finally break through the line, they first jump to distant defects. When all the defects are occupied, vortices begin to enter interstices. The interstitial vortices hop from one interstice to another as far as vacant interstices remain. Vortices are hopping from one interstice to another. When all the interstices are occupied, a different kind of flow appears. Because the vortices cannot find any vacant side to hop to, they continue flowing in a single line. All the vortices in each line move simultaneously.
So what you have seen is that these fluxon, the Abrikosov flux punching through a thin film of superconductor, is now dynamical. They can move around. And if the film has a defect in it, the first part of the video showed that defects tend to attract those vortices. The vortices get trapped where the defects are. But once you have more and more vortices coming into the system, not all of them can occupy the position of the defects. They sit somewhere in the middle. But once they're bunched together because they repel each other, then there's a traffic jam going on. But if you further keep putting in these vortices, the traffic jam has to somehow move because there are more and more coming in. So this is a situation of almost bumper to bumper. The new coming cars would push the other cars in front of them, and the whole thing start to flow like this. So that's what we have seen here. So let me
We
play
are
this
looking
again.
at an array
So
of
when there are
defects.
defects, they
When
tend
the
to
magnetic
attract
field is applied,
vortices.
vortices are produced from the upper film edges, and the front row of defects is soon occupied.
Right.
However, subsequent vortices cannot easily pass through the front row.
That's because of
When
repelling
the
force
vortices
among
finally
vortices.
break through the line, they first jump to distant defects.
So this is the traffic jam now going on.
When all the defects are occupied, vortices begin to enter interstices.
So they have to be
The
somewhere in between
interstitial
these
vortices
vortices.
hop from one interstice to another.
So there's
as
still
far
room in
as
front of the traffic
vacant
jam, so they just
interstices
go ahead
remain.
and move to new positions.
Vortices are hopping from one interstice to another. When all the interstices are occupied, a different kind of flow appears.
So this is a
Because
situation
the
now,
vortices
the entire
cannot find
freeway has
any
become a
vacant
parking
site to
lot,
hop
right?
to,
But still new cars are
they
coming in.
continue flowing
So the
in
new
a
cars
single line.
push all the cars in front of them, and you see this
All the
flow.
vortices in each line move simultaneously.
So that's what you observe in this video. And you're welcome to check out this the YouTube site yourself and watch it on your computer. And this is really incredibly interesting. So this is Fluxon. So magnetic flux does penetrate into a superconductor if it's type 2 superconductor for certain properties. And they form a triangular lattice if it's actually bulk material. But if it's thin film, these magnetic fluxes can move around because it doesn't have much of a depth in a thin film, and it's called the fluxon. And fluxon repel each other because it's type 2 superconductor, and you see this kind of behavior because they all repel each other. They form this, they get attractive defects, they get stuck. There's a traffic jam, and the traffic jam being pushed through by the new coming the fluxons, and that's what we have observed in this video. So it's really interesting to watch this kind of phenomenon. And once again, this is a highly quantum material made up of the condensate of the Cooper pairs of electrons. But you can really understand this video intuitively just by knowing that you can solve the classical field equation to find these solutions with the magnetic fluxes. And if you have a thin film, each object becomes like a particle, it's a fluxon. We know they repel each other for type 2 superconductor. Then you can understand what's going on in this video very intuitively and using classical field theory now. And so that's the beauty of the quantum field theory. So highly quantum material can be described using classical field theory, as we have seen in the case of BEC. That gives you explicit solutions you can work out in your computer. And those solutions is something you can see in front of your eyes in a lab experiment. Then you can understand their behavior because they repel with each other. And so that's what we have seen here. So Riley thinks it's cool. Great. All right.
Oh, I have a question about the
Go ahead,
video.
Riley.
So the more fluxons are appearing because the magnetic field is still being applied.
Yep.
And so when we saw the traffic jam of the fluxons moving in a line, that was because more fluxons are being added still because of the magnetic field. So where are the fluxons at the bottom going? Is the film just longer at the bottom?
That's a good question. I actually don't know. So I think they drop off from the film. So magnetic field now escapes the superconducting film. I believe so.
Okay. And so then there should be like a maximum number of vortices or fluxons that could fit.
Yeah, because if it exceeds the maximum number, then the superconductivity breaks, as you saw on the phase diagram.
Okay, cool.
So there's some limit to how many magnetic fluxes you can pack into the system. Okay, any other questions? Once again, I emphasize, you can understand this highly quantum behavior material using classical limit of the quantum field theory, and you can just use your own computer to look for the solution in classical the field equation and describe this behavior of the material. And that's the power of the quantum field theory you are learning this semester. Okay. All right, so that's the superconductivity. Now I'd like to, oh yeah, and this is also something you might do in a lab experiment. You see this, the thin film of superconductor floating on a piece of magnet, and that's an experiment that's often described in a superconductor. And this is again a situation where magnetic field coming from this permanent magnet is punching through this material, and that's why it actually becomes stable like this. So fields are punching through it, so you can actually change the orientation very easily, and that's why it keeps flowing even above or below the permanent magnet. So let me just do this once again. So here, the magnetic field is punching through this the plate of superconductor. There's nothing in between, and the superconductor is not a magnet. Even if you flip it around, it still floats, and even if you turn it around, then it still sticks with the magnetic field because the field is punching through it. So it's sort of being caught by this web of the magnetic field. And so the whole piece levitates. And this is what you actually use to build a maglev. So when you have this fast train going at the speed of something like 300 miles an hour, you don't want to have a rail on which the train moves. That would be very uncomfortable. But it's floating using this magnetic levitation, then you can be riding the train comfortably. And that's the idea of the maglev. It's always floating. And you use that, actually, this superconductor to make that happen in a very power efficient fashion. And so that is, again, a quantum phenomenon being useful for the society. So that's the idea of this the superconductor. Okay, so I'm running out of time today, but I'd like to actually put this in a context. We talked about fluid, superconductor, and we also would like to talk about a piece of magnet as time goes on. And all of them are based on this idea called spontaneous symmetry breaking. So as you all know, Emmy Noether proved this theorem, Noether's theorem, that the symmetry of a system leads to a conservation law. And later on, we also learned that the conserved charge generates the symmetry. So it goes both ways. Symmetry leads to conservation law, and conserved charge generates the symmetry. And let me tell you what I mean by this second statement. So you have seen this Hausdorff formula in one of the homework problems with the Bogoliubov transformation. So you can define a symmetry as a unitary operator acting on the Hilbert space. And symmetry has to be unitary so that the probability doesn't get changed. So what is meant by this is that when you have the translation symmetry, and you learn in classical mechanics class that will lead to a conserved quantity, namely the momentum. Translational symmetry of space is what leads to the momentum conservation. Now you have this momentum operator in quantum physics, and what you do is put the momentum operator into the exponent to define the unitary operator of the translation. So that is what I meant by the symmetry generating the conserved quantity generating the symmetry. Once you have a conserved quantity, according to Noether's theorem, in this case momentum, exponential of the momentum gives you the translation operator. So that's how it goes both ways. Rotation symmetry of space leads to the conservation of angular momentum. Putting angular momentum in exponent gives you an operator of rotation. So once again, conserved quantity generates the symmetry. So the word generate means the conserved quantity gives you infinitesimal version of the symmetry. If you put that in exponential, that will give you a finite rotation. So that's the meaning of generating the symmetry. And we also have learned that invariance of the theory by changing the phase of the field leads to the conservation of the number of the particles. If you put number operator in the exponent, this is what generates this phase transformation symmetry of the theory. So same idea. So whenever you have a symmetry, that leads to the conservation. Something you may not have seen before is that you can also think about a discrete symmetry. So inversion of space, that's parity. You cannot do this infinitesimally. You have to do it all of a sudden invert the entire space. That's the idea of parity. But even that kind of symmetry would lead to a conserved quantity. Parity is an operator that squares to 1, because if you do it twice, you haven't done anything. So now you have defined a new conserved quantity called a parity operator, which can have eigenvalue +1 or -1. It turns out that every elementary particles have the parity eigenvalues, either +1 or -1. In this case, the parity operator itself is Hermitian, but also unitary, because if you take parity dagger, it's Hermitian, it's the same thing as P itself. And if you multiply this with a dagger, namely P itself, that's P squared, we know it's 1. So it's Hermitian, but at the same time, it's also unitary. So this parity operator is what generates the symmetry as well. So the same idea works even for discrete symmetries like parity. For every example, you have a symmetry that gives you conserved quantity. And conserved quantity generates the unitary operator of the symmetry. So that's how the Noether's theorem works in quantum systems. But the reason I'm reviewing this is that when you have psi, which has a condensate, psi has a expectation value in the ground state with a particular phase. And that led to this interference fringe pattern of the Bose-Einstein condensate. What it means is that this symmetry of arbitrarily being able to change the phase of the field is now lost in a given ground state of definite phase. So that's the case when you say a symmetry is actually spontaneously broken. So what is common between superfluid and superconductor is that this symmetry of changing the phase of the field is now spontaneously broken. And there's a consequence for that. So what I would like to do next is basically wrap up all of these discussions about the weird condensates we have been talking about according to a single concept of spontaneous symmetry breaking and trying to get a big picture of what's going on. And so I'd like to go through this discussion next week. And that discussion will be somewhat qualitative. There will be no the homework problem associated with this concept. So we actually, maybe a conceptual question I might ask. But anyway, so I go through this using actually a colloquium I have given elsewhere and go fairly quickly, but just to give you a big picture of this idea. So that's the discussion that's coming on next Wednesday. Okay, so I ran out of time, so let me stop here. Are there any questions? I already lost people. Is that okay? All right, so good luck with the rest of the midterm, and I see you on Wednesday.
Thank you.
Have a good
Bye.
weekend.
Thanks, Professor.